Hey.
Okay.
You get the
So
diagram.
here we go. We're just designing a box here, and it says the compartment must be 2 meters longer than it is wide. So it defined length in terms of width. So length in terms of width. 2 meters longer than it is wide, 2 plus W. So since we define length in terms of width, W will be our variable. And then it says its depth must be 1 meter less than its width. So the depth of this is 1 meter less, so W minus 1. Now, could I put W plus 2 instead of 2 plus W?
Yes.
Sure. Either way, whatever suits your fancy. All right, write an equation to model the volume of this compartment. So volume of a box is length times width times height. W times W plus 2 times W minus 1. But it says that the volume must be exactly 8 cubic centimeters. So what can we set this equal to? 8. And so if we set this equal to 8, and we wanted to solve this. Oh, thank you. What we have here is a cubic function, don't we? Right? So if we were to multiply these two, we'd obviously get W squared minus 1W plus 2W is plus W, and minus 2. And then we just distribute the W, but we obviously have to move the 8 over. So we get 0 equals W cubed plus W squared minus 2W minus 8. That W cubed doesn't look like a cube. Let me try again. Slightly better. Okay, so now we have the equation that we're going to solve. So this equation here models the volume. And this specific example, they want the volume to equal 8. So to solve this, we set it equal to 0. That's how we solve polynomial functions. Part B asks us to list all the possible rational roots. Okay, so from last week, how do we find the possible rational roots?
The factors of 8 over the factors of the beginning thing.
Very good. All the factors of 8 divided by all the factors of 1.
Can we just call it beginning thing?
That is what the leading coefficient is. It's the beginning thing. All right, so all the factors of 8. That would just be 1, 2, 4, and 8, right? Okay, we know how to test these algebraically, but we also learned that we can test them using our calculator and just look. So take out your technology, which we'll be using for the rest of the class anyway, and let's see which one of these rational roots, possible rational roots, is actually really a rational root. It's any of them. These are our possible. Let's see if any of them work.
Whoa.
Does it bother you here?
I feel like I did something wrong.
Did you get 2?
My window is, for some reason, 1,000 by 1,000. I don't
It
know
makes
why.
for an interesting looking graph, doesn't it?
Yes, it does. It makes for a line.
Zoom 6 and see if you can see where it crosses.
I'll just set the window to 20.
It crosses at 2. All right, do you see if it crosses any other place?
Nope.
No, we currently don't see any others. But what could we do algebraically to determine if any were there? Synthetic division. All right, so we know that 2 works. We just discovered that. And now we're going to see if anything else will work. So 2 is a rational root. We'll put our coefficients here. 1, 1, negative 2, negative 8. and we'll synthetically divide. So to synthetically divide, you always bring down the first. You multiply, you add. You multiply, you add, you multiply, and then you have a party, because it worked.
Is there an imaginary?
Let's see. What we're left with is a quadratic. We would hope it would factor. We're sad that it doesn't. So we have to use quadratic formula.
Oh my god.
So if there are any more real roots, they have to be irrational, right? Because it doesn't factor. So let's try it. Negative b plus or minus the square root of b squared minus 4 times a times c, and we can already tell it's not irrational, it's complex because there's a negative under the radical. All over 2a. So my other two roots are, this is negative 7, so it's I root 7. So my rational root that worked was 2. And if I asked for all roots, you would also have to give me that negative 3 plus or minus I root 7 all over 2. But this isn't a real root. So would it be a dimension?
No.
No. This was my answer this problem was looking for. Just the 2.
I was gonna say.
Okay?
How do
So-
the irrational
That's a great box.
affect like a shape?
What an irrational would end up giving us would be like a decimal. So if it were like the square root of 3, one of our dimensions would be 1.71.
No, but like if it had like an I.
Oh, an I in it? That is not a link.
But like, wasn't there a graph we had and it was like a big
Sometimes
like a
those are causing something else to happen in the graph, but just not at the x-axis. Okay. So what are the dimensions? This compartment would be 2 meters by, let's plug in our 2, 4 meters by 1 meter. Those would be the dimensions. That's a fairly large compartment, isn't it?
yeah.
How big is that?
A meter is very similar to a yard.
And a yard is
How big is a yard?
3 feet.
So about this comment, we watched a movie
Okay.
and Interstellar. I was supposed to those movies.
Alright.
That movie was amazing.
Okay, I have a few additional problems. You're probably going to just want no big paper. I've printed the problems for you, but there's no room on here to do work. But at least this way you'll have your own copy of the problems if you go to look at them later.
Start homework? No.
No, the homework is the back of page 119. It's page 120. You certainly may. It's yours to keep, but it's not in the room. Please do not lose this half sheet because the back of it will be an assignment for a different day.
In order
I don't know any of the words.
Okay, go ahead and read the first question. That's because you're awesome. Okay, so everyone should have. Doug, did I get you one? Everyone should have the word problems. Let's read the first one. The first one says, here we go. A farmer has 1,600 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fencing along the river. What are the dimensions of the field that has the largest area? So this kind of ties into things we've already done. We have this river, and this farmer is going to fence off alongside the river. And it said straight, so I guess it really wouldn't have those. There we go. So we really only need fencing fencing here and here and here. And it says we're creating a rectangular field. So there we go. We want the dimensions that give us the largest area, where area of a rectangle is just length times width. And if we want the largest area, what are we trying to do with this function? Largest tells us we are maximizing that area, right? Okay. So all we know is we have 1,600 feet of fence. Where do we go from here?
Yeah, it's long end or short end.
Yeah, you're right. You don't know what this dimension or this dimension is.
You just guess. So
Well, if we're trying to find the max, then we would probably assume it would be the shortest.
No.
So this short end, what do you want to call this short end?
Yeah.
A? Okay.
I always want names.
So what would we call this?
Can we call it L and W?
Okay, A and B.
Wait, is A supposed to be the long end or the
But A's
short
area,
don't
so you
know.
can't label it A, can you?
If you labeled it A, you do lowercase a. I probably would have called it X, but X is just my favorite variable in math.
I would have just gone with L.
I'm doing, yeah, that's what I'm doing.
I always do X because then I do my little like cool X looking thing.
You want to go with L and W? You want to stick with two different variables.
I want to go with uppercase X and lowercase x. Actually, better yet, uppercase I and 1.
I think this really quick problem is going to take a lot longer.
Alright, here.
Okay, so far we've completely ignored the fact that we have 1,600 feet of fencing. The problem gave us one number. Let's use it. How can we use it?
To W or L, whichever one, plus the other variable equals 16.
If I stick in terms of two variables, it makes the problem much more difficult. I'm calling that X. You can call it W, you can call it A, you can call it whatever you want. It's X on my paper. Alright, so if this is X, what is this in a rectangle?
Also X.
That is also X. So now I've used up X feet of fencing and another X feet of fencing.
1,600 minus 2x.
Thank you, Doug. So that leaves 1,600 minus 2X.
Whoa. Sorry.
Alright, so whatever variable you chose to use, you could have used any of them. A, B, L, W. It doesn't matter. We end up with the same thing when we got here. So in this case, area is X times 1,600 minus 2X, which is 1,600X minus 2X squared. Okay, this is not much of a higher degree polynomial function, is it? What kind of function is this?
Fine, nobody.
Quadratic.
I don't know. You can do
It's a quadratic, isn't it? We could, and that would take me back and take me right back to the zeros, wouldn't it?
It knows that.
That would be helpful, but if we are maximizing area, this quadratic is going to open which way? Up or down? Down. Down, because the square term is negative. Okay? So the maximum area is going to obviously occur at the vertex, because the maximum of any quadratic occurs at the vertex. And because this one opens down, that gives us the max.
It's in graphs.
Now, you said a minute ago this would give me the zeros, and it sure would. And so if you remember from graphing an intercept form, we know that the vertex is always halfway in between our two x-intercepts. So this would occur at 400, correct? Now if you didn't remember that, hopefully nobody in here has forgotten that the x value at the vertex is always negative b over 2a. So we have lots of ways we could have solved this one. So that would be negative 1,600 over 2 times negative 2. Negative 1,600 over negative 4 is 400. Is that the same thing I got a minute ago? Yes. So I know that x is 400. So if this is 400, what's my other dimension? 800. So it's 400 feet by 800 feet. Those are the dimensions of the field that would maximize the area, given that length of fencing. Okay, any questions?
What did you,
Okay, go ahead and read number 2 and see if you can draw out a picture for yourself. Okay, so we're creating a box. This box does not have a top, but we're starting with a square piece of cardboard. The company wants the height of the box to be 3 inches. So if we're taking this box and we're creating a net, what we're going to do is we're going to cut out little squares out of each little corner. And then when we fold them up, we're creating a box. Now, obviously, this is not the only way to make a box. You've seen lots of different types of boxes where you would just cut one side and then glue and flap and whatever. But this is how we're creating our box. All right, it tells us that the height of this box is 3 inches, so it gives us this. Because when we fold this part up, that's what gives us the height of the box. So we know volume is length times width times height. And we know the height is 3. And we know the volume is how much? 432. But what we don't know is the sides, the length of the sides of this square. So what do we use when we don't know something? A variable. So what variable would we like to use for the original length? X. Okay. But it's going to be minus something because we're cutting out a square here and we're cutting out a square there. So it's x minus what?
6.
6. So since this is a square box, both of those dimensions would be x minus 6. So I write x minus 6 times x minus 6. Or x minus 6 squared, right? Times 3. Now we could set this equal to 0 and solve it like it's a quadratic, but it divides by 3. It's much easier to do this algebraically. If we divide both sides by 3, we get this nice little 144 equals, aren't there 2 x minus 6's?
Mm-hmm.
Could I write that as x minus 6 squared?
Yes.
And then in this particular case, it's pretty easy to take the square root of both sides. Now when I take the square root of 144, I get positive or negative 12. But in terms of this problem, I'm only looking at positive 12 because I'm looking at dimensions, and a negative dimension makes no sense. Doesn't exist. So I get 12 equals x minus 6. So what is x?
18.
X is 18.
Wait, can you actually make a box like that? I've never tried to do that.
I mean, it's not going to
Yeah.
have a top, but it, yeah.
Never tried
What
to
kind
do
of
that.
company is putting this much work into making a box?
So they count
Harry, one of my friends from Georgia Tech, when he graduated, got a job at a box making company.
He's a box engineer.
He was, and he changed some of the ways that companies made boxes.
Really not.
I have another this morning.
And then fold up the four class.
This week I haven't been calling.
Folding up.
You're gonna be a box
Maybe
engineer.
a box specialist.
Yeah. Pretty awesome. All right, maybe Amazon would hire you. They deal a lot with boxes. Okay, so what are our dimensions here? It is 18 inches by 18 inches.
Is that a box drone? Amazon.
By, okay, this is the cardboard. This is the cardboard that we start with. But the box itself, what would the dimensions of the box be? It would be 18 minus 6, which would be 12 by 12 by what's the height? 3. Those would be the dimensions of the box. Okay, so these are the answers to part B, sorry. What size piece of cardboard should we start with? 18 by 18 inch. And then the box ends up being 12 by 12 by 3. Okay, we're going to skip number 3 on your worksheet for right now, and we're going to move on to number 4. It's another box problem, but it's a little different. We're once again creating an open box. We're starting off with a rectangular piece, and this material is 15 by 9. And we're still cutting equal squares from the corners and turning up the sides. But this time, they don't give us the volume. They're asking us what would the dimensions need to be in order to maximize the volume of a box. So volume is length times width times height. And we're starting out with a 15 by 9. But then we're cutting out the corners. Okay, so what does our variable represent in this problem? Yeah. So if this is x, this would be x. So we know our height is x. We good with that? All right. Now, once we create the box, this is our length, and this is our width. So what's left for the length?
15 minus 2x.
And the width.
And 9 minus 2x.
Very good. So my dimensions are x times 9 minus 2x times 15 minus 2x. So some of this we could do without our calculator, couldn't we? It's already factored. Where are my zeros? Zero.
9 pounds and 15 pounds.
Very good. 4.5. And then 7.5. What is the left end of this function doing? Is it rising or falling? It's odd and positive, isn't it? So it's going to fall to the left, rise to the right. Is it passing or bouncing? Pass. Pass or bounce?
Pass.
Pass, pass or bounce?
Pass.
Okay. So, in terms of this problem, what is a reasonable domain for this function?
1.
Well,
Okay, for the function, yes. But in 0 to what? 0 to 4.5. Because from 0 to 4.5, this box actually has volume, doesn't it?
Yeah, 0 like
Down here, the volume would be negative. So it doesn't really exist down here.
and below
Why?
is
Why would it not exist down here?
Because
it can't have a volume.
Because that dimension would become negative. Can we have a negative dimension?
No.
No. So when we get problems like this, we have to think about a reasonable domain in context of the problem. For us, it's going to go from 0 to 4.5. It can't equal 0 because then we'd have no height.
And you can't.
And it can't equal 4.5 because then we'd have no, whatever we call this, width. Yes?
What about the 7.5 and on?
Okay, it has to be between 0 and 4.5, so 7.5 isn't even in the picture. The only part of this graph that matters is what I highlighted in green. In context of the problem, nothing over here and nothing over here exists.
Would there be a problem where, like, it would keep going and go through again, and then you have to choose one?
As long as it violates one dimension, even though it's positive over here, 10 won't work, because 10 gives me a negative dimension. If it violates any of them, then it doesn't work. So, our domain has to satisfy each of the factors. Okay, so if we want to maximize this volume, what we're looking for is, where's the max between 0 and 4.5? Calculators? Actually, the bell's going to catch us, so here's my calculator.
It's like 2.7 something.
All right. So this point right here occurs at 1.82. So we'd punch in 1.82 for x, and then this would give us the dimensions. We have to subtract here and here. Make sense? Okay, now, how would this problem change if they told us what they wanted it to equal? Well, we just set it equal to that. We already had this part typed into our calculator just a second ago. All we do is minus 56 and look for our zeros. Now, once again, the only zeros that matter are those that fall within the reasonable domain. Anything outside the reasonable domain does not exist in terms of this problem. So this problem says which of these values is a physical impossibility? The 8 is. Even though it's a 0, a solution to the equation, it's not a solution to this problem because it doesn't fall within the reasonable domain. Okay. All right. So your homework is to finish up the back of the workbook, page 120. Not hard. We'll practice some more word problems again another day.